projects. In this video, we are going to explain about a project titled A Method for Sensor Reduction in a Supervised Machine Learning Classification System. The project presents a technique to reduce the number of sensors in a supervised machine learning classification system. This method is specifically designed for cost-effective solution in market where interconnected smart devices with multiple sensors are widely used. Instead of relying on multiple sensors, the proposed approach utilizes a single sensor that generates a time series output. Expert knowledge is applied to discretize the output into distinct intervals representing the different events in the system. Statistical measures are then computed within these intervals to serve as features for the machine learning system. Compared to the traditional sensor classification system, this method offers the significant cost savings by reducing the sensor count and simplifying the algorithm development and testing process, while still maintaining the robustness. The project objective is to present a technique for minimizing the number of sensors needed in the supervised machine learning classification system, specifically targeting the cost-conscious solutions in markets where interconnected smart devices with multiple sensors are prevalent. The proposed approach capitalizes on the time series output generated by a single sensor and employs the expert knowledge to categorize the output into distinct intervals that align with physical events in the system. This method offers a more cost-effective solution compared to the conventional sensor classification system, not only by reducing the sensor count but also by streamlining the algorithm development and testing process, which is resulting in improved simplicity and robustness. These are the requirements that are needed to build this project. Hardware requirements are operating system as Windows, processor of i5 and above, RAM of 4 GB and above, hard disk of 20 GB and above. Software requirement: Python IDE with version of 3.7. These are the modules that are developed to build this project. The first module is Upload the Sensor Dataset. This module allows the user to upload the sensor dataset to the application. The dataset contains the information from smart devices such as printers and smart mobile phones. The dataset includes the multiple sensor data which will be used to control the output of the devices. And the second module is Generate the Train Test Mode. This module passes the uploaded dataset and generates the train and test set for the LS-SVM algorithm. The dataset is divided into two parts, that is 80% for training the model and 20% for testing the model. And the third module is Run LS-SVM algorithm. This module applies the least square support vector mission algorithm to the training dataset. This algorithm is used for multi-class classification where a single record may belong to multiple classes. This algorithm finds the solution by solving a set of linear equations rather than a convex quadratic programming problem. And the fourth module is SVM with sparse matrix. In this module, the sparse matrix feature selection algorithm is applied to reduce the number of columns or features in the dataset. The sparse matrix algorithm evaluates the similarity between the features and selects only the relevant and related features. By reducing the feature size, the training time and the prediction accuracy of LS-SVM algorithm can be improved. And the fifth module is Classifying the New Records. This module allows the user to upload the new record, that is test data, from the sensor. The LS-SVM model trained in the previous modules is applied to predict the output values for the new records. The predicted output value determines the settings to be adjusted for the printer based on the censored data. And the sixth module is Classification Graph. Using this module, a classification graph is generated to visualize the predicted output values for the test records. The graph helps in understanding the classification result and the distribution of different output values. And the final module is Extension Comparison Graph. This module compares the performance of LS-SVM algorithm with and without the sparse matrix feature selection. This comparison graph illustrates the difference in prediction accuracy between the two approaches. This analysis help in evaluating the effectiveness of the feature selection technique and reducing the training time and improving the accuracy. The execution of this project. To execute the project, first we need to open the code folder. This is the code folder consisting of different files. The first folder is dataset folder consisting of the dataset and the testing dataset, and that is image folder consisting of different images, which these are used as the buttons for the graphical user interface. And these two files are of code files, and this is the run.bat file. Instead of executing the program in command line interface, we created the Windows bat file to execute the project. Now to run the project, double click on run.bat file. Here, this is the graphical user interface. With this, we are interacting with the program. First, we need to click on Upload the sensor dataset. Using this button, we are going to import the dataset from the corresponding folder and click on Dataset file and click on Open button. Here we can see that the dataset is loaded and the number of features that are present in this dataset is of 23, and then click on Generate Train Test Model button. Here, this is used to read the dataset and generate the training and testing model for the classification. Here, the number of features that are present in this dataset is of 23 and the dataset length is of 539, and the dataset is divided and splitted into the training and testing part. Here, the training length is of 431 and the testing length is of 108, that is used to test the model. And then click on Run LS SPM Algorithm button. Here, by this, it generates the LS SPM classification model on training and testing data, and it gives the classification accuracy of 72.22. And then click on SVM with sparse matrix button. Here, the sparse matrix LS SPM is generated with of training and testing data. It gives an accuracy of 86.1. It is done by using the feature selection algorithm. And then click on Classify the New Record button. Here, we need to upload the test data and predict its output. Here in this screen, the first record output is classified as card stroke, which means the printer has to adjust itself to the card stroke setting. And this way, the second record is classified as light. In that way, the printer has to adjust itself to the light setting. In this way, we can adjust it automatically. And then click on Classification Graph button. Here, this is a bar graph where the x-axis represents that of light, normal, heavy, card stroke and transparency, and the y-axis represents the number of records classified in that class. And this graph, the light class gives an 8 records, whereas normal class gives of 5 records and that of different classes. And then close this bar graph and click on Extension Comparison Graph button. Here, it gives an comparison graph by comparing the two algorithms we used, that of LS SVM algorithm and LS SVM with sparse matrix. And this way, the y-axis gives the values assigned for the accuracy of each algorithm, and the x-axis the algorithms we used. And then close this graph. Finally, the project concludes that the proposed methodology for leveraging the domain expert knowledge and temporal data for the design of an Internet of Things system resulted in a highly robust and accurate system with reduced cost, size, and complexity over traditional approaches. The methodology was demonstrated in a case study of a mass-produced electrophotographic printer in a system designed to classify the media type. The proposed methodology increased the classifier accuracy by 16% and classifier acceptability by 6.1% when compared with the more traditional method that did not leverage the domain expert knowledge to enrich the dataset. The methodology used can be applied to sensor-integrated IoT devices seeking to benefit from the performance enhancement associated with today's modern sensor technology while still meeting the various market constraints.
Thank you for watching video. For more projects please visit our website www.trueprojects.in. For updates on latest project videos, please visit True Projects YouTube channel and subscribe.